some training of the differential relays, the usage, the breaker failure sync, and recloser relays. So starting, we will go ahead and just see the outline we are going to talk about, which is, as I said, the transfer relays, breaker failures, and sync check relays, plus auto relay. But the question comes, why we need the differential relay and when we need differential relays? Now, differential relays are for the transformer, to protect the transformers. And why is the transformer? Why you need it for the transformer? You know, since the transformer is the heart of each station, it's the heart between the generation to transmission, transmission to distribution. And it's the most, let's say, expensive asset in the power network. We should protect it and keep it healthy as much as we can. You know, having a failure of line of protection or line trip doesn't mean that we will have a problem that we cannot feed the other station. But if we have a problem with transformer, it means that maybe a generator will not work for some time until we replace the transformer or fix it. In some cases, that the transformer may have a blackout, station goes blackout because transformer. That's why we have to take care of it and have the right protection and the right configuration for the transformer itself. Now, we have a lot of transformers starting from distribution up to the, main generation and transmission. The MVA is, let's say, huge. I have seen 1,200 MVA here in Saudi Arabia, but there are maybe more outside, which I'm not sure about. But basically, we have a lot of protection for the transformer itself. And basically, the differential relay, usually we are using it for the rating of 5 MVA transformers and above. Below that, we are using sometimes overcurrent and other protection that we will also go ahead through. But let's talk about the transformers first, the types we have commonly used here. No, it is different from transformer to transformer depending on the purpose. Maybe sometimes step up or step down. As we know that generation, if we needed to transmit it, we have to step it up, and then again in the distribution we have to step it down. But also we have another factor like the Victor group. And then is it one phase or three phase? As I told you, 1,200 MVA transformer, that was a single phase transformer, not three phase. There are some auto transformers, winding. We have 2 winding or 3 winding, depending on the usage. Like, for example, in say 80 kV substations, we have a tertiary transformer usually, which is 3 winding. The tertiary will use for powering up the station. And sometimes they use it also to give a power to, let's say, another distribution station. So it depends on the configuration and where to use. But everything is different, so protection here is different. And then we have to calculate it really right. Otherwise, we'll end up with, let's say, blackout or tripping, unnecessary trippings. Types of the faults, we have it, which we call it internal faults in the transformer itself, and we have external faults. External faults shall not affect my transformer, shall not affect my transformer protection. But internal fault, we need to isolate it very fast to save our transformer and the network. Now, the faults commonly inside the transformer is insulation breakdown, like the oil, or overheating, excitation, or let's say oil contamination or leakage. So these are something that happens inside the transformer, and we need to see these, and we need to protect the transformer against those things. This is something that is happening, like term to term, sometimes it's very, very low that you cannot see it, but we have other devices to protect it. An example is that we have 2 major things we are going to talk about, which is the mechanical protection of transformer and the electrical. So I'll just go through the mechanical protection very fast, just to show you what we have in the transformer, especially our transformers. The main relay is the Buchholz relay, or what we call the gas relay. And I have brought a picture here to show even the location, because the location is between the conservator to the main tank, and it is detecting oil if we have a low oil, or let's say if you have a gas, a lot of gas because of interturn short inside. This relay will have two contacts mainly. One for alarm to alarm the operation that there is a problem, and this contact will trip the transformer in case of a problem inside the transformer. We have another one which is called sudden pressure. The sudden pressure, usually they put it in the top of the transformer, and whenever you have a sudden increase of the pressure inside the transformer, this will blow up and will trip directly the transformer to protect it against anything. So that's another thing that we are using in the transformers. Now we have some other things like the oil and the winding, and both are working together actually. So oil, it will look always at the oil level, and then will give you an alarm and the trip. In some cases, there is no trip if it is monitored station. And the winding temperature actually will do 4 stages, let's say, in our case. The first stage will maybe start the fans. Second stage will start another fans or motors, or let's say the pumps. And then in some cases, we'll have an alarm, like the third stage, like an alarm to the control center that you have a problem overheating. And the fourth stage will be the tripping. So we can have still a trip, and we don't need to have a trip if it is monitored station. So it depends on the location. You may have a trip or you may have not. But internationally, yes, the fourth stage of the winding temperature will give it trip directly to the brake. Now for the electrical protection, we have a lot, but I'm just defining some of them here. The main topic, which is for our webinar today, is the differential relay protection. So we have flushing relay, we have over voltage, under voltage, neutral imbalance, restricted air fault, backup overcurrent, and those overcurrents will be directional or non-directional depending on the transformer. So even there is more, but because of the time, we are going to talk about some of them today, which is the main topic, which is differential protection relay. But let's go through the differential relay and let you know the principle of operation, like basic principle of operation. So in a normal condition, that we have same transformer, let's say, power flow from one side to the other side, and my CT here will have the secondary current going to my relay over there, depending on the polarity, which should be right. And then we'll have I1 and I2 canceling each other by 180 degrees. This means my transformer is stable and we are delivering the power to the customer. In case we have an external fault, it should be the same, that my I1 and I2 should cancel in the operating coil and nothing should happen. And my transformer should be healthy because that is far away from transformer. Unless otherwise we have some issues with the CT ratios or with something that we'll talk about it also later on. Now, if we have an internal fault, now this is where my transformer differential should work. Now, both CT polarity being changed and both of them are the same direction, means they are 0, both of them, degree adding to each other, which shall trip by my transformer differential. This is the basic operation. Of course, with the new relays now, we have restraint over here and restraint over here, a lot of things, but that is only the basic principle of differential relay. Now, I've told you that there are some challenges that we are talking about, like the CTs here over here. If it is, primary and secondary, usually it's different currents or different CT ratios. Maybe MAC curve is going to be different. So a lot of things that we have to think of, which is going to affect even the transformer protection. Now, this is some of them. I have put it here, like the current mismatch caused by the transformer ratio, the current mismatch caused by the different CT ratios. So transformer ratio is something, the CT ratio is something. Delta Y connection, zero sequence, LTT even. When you have on-load tap changer, you are doing some changes now, is it going to affect or not? The harmonic, of course, that is something always we'll have when we start the transformer. overexcitation phenomenon, which is coming from over voltage in the network, and switch on to fault function. So these are some of the functions which is affecting, and we have to take care of it during doing engineering of the transformer protection, or let's say troubleshooting if we get a problem with transformer differential relay. Now, how to test these? By the software which is provided by Megger, which we call it RTMS. The RTMS can work with both Fraser units and the smart units, and it is three-phase test equipment that, it's three-phase testing that you can perform or require differential relay testing. So, first test, it will do the stabilization test, which is very important for each, let's say, each test engineer or maintenance engineer to know that my secondary side is stable, my connection is right, and the relay setting is right. So this is something that it will affect all the tests if you have a problem with the stability in the first time. Then the basic test we'll go with, like timing test and pickup test. This is usually the basic test for the transformer differential, and then we have some advanced like slope test and harmonic test. And those in the right side are the tests which is going to be done by our software automatic. We have also something for the generator and motor differential relays. Those are a little bit different than the transformer because we have no harmonic over here. So we can test the stabilization, timing, pickup, and slope characteristics. So those only the thing, this is the only difference between the transformer differential and generator and motor. And this is the software. When we started, we had the three icons over here. So that's for the transformer, the one which will have harmonic, and these two will not have harmonic. Now, when we click on the software, it will pop up the main settings screen that we need to put all the settings carefully, and we should make it right according to the relay and according to the transformer. So, if everything we put it right in this case, the first test we'll go with, as I said, the stabilization test, which will allow us to know that my connection is right, my setting is right, and it will allow us to put the, after injection, we can write all the data over here, which we can read directly from the differential relay. And this will be recorded, and we'll have it also in our test format. Now, the first test we will talk about here is the pickup test. Now, the pickup test, what is the what setting is required for the pickup test? Of course, all the transformer needs the setting of the primary and secondary MVA and the vector group, which is common for all. But the pickup single phase pickup factor is very important also, and that is defined like when you have a delta Y, and when you need to put the pickup factor like 1.73. In some cases it's 1.5. So it depends from relay to relay, and those are written in the relay manual usually. And then the other thing is the pickup setting here, which is per unit. Usually they give it for the protection relay. So these three things are necessary to do the pickup test and to make it right. After you select everything right, pickup test will go through phase to neutral and three-phase. And notice here that because we have a delta Y, then we have different pickup in three-phase because the factor is only for single phase, not for the three-phase. So this is the different calculation over here for that. Now, next test is the timing test. Now, the timing test, we need the pickup value as we have done, but we need also the trip time over here, which is very important because it's usually 0 milliseconds. Some cases it is 50, some cases 100, depending on the transformer relay and engineering being there. So usually we inject more than the setting value which we are putting here, so that we'll have the timing right. So, and usually it should be less than, as I said, we put usually 50 milliseconds as default here. That's because it should be like that, but in some cases I have seen they put 100 milliseconds trip time for transformer differential relays. Okay, so after putting this setting, we can do directly, we can go to the menu, and then we can do the timing test, which is we will have something like this: expected time, setting time, and then the measured time. So two tests being done now, like the transformer pickup and transformer timing test, or transformer differential timing test. Now, for this loop, we need other settings that are affecting this loop here. So it's not only the pickup value and pre-fault value, but we have this over here. This is going to affect depending on the loop characteristic and restraint equation, and both of those from relay to relay are different. We can find them in our help, and then also you can find them in the relay manual. Sometimes it's not written in the setting, so you will not know it in the setting, unless otherwise you are expert and you know where to go. Now, we have the 4 segments over here that you can go ahead, like for example, line segments, slope through origin, any slope. So these 4 slopes are the common used by all the manufacturers. But sometimes the same manufacturer use 2 slopes in 2 different relays. So you have to be very careful when you choose the slope. Now for the restraint equation also, we have a lot of restraint equations you have seen here. The issue is that which equations you have to use. Again, it is the manufacturer, and again, when you press on our help, we put already something like, this is for these relays, we are using this equation, this relay uses this equation, and this relay uses this equation. But again, that's also something that you can find in the manual of the relays. Now the slope characteristic will come like that. We can put up to 10 points to test, and then we'll test it as 3-phase shots. After the slope, we will do the harmonic. We can do, of course, the second harmonic, and then we can put 5th or any harmonic. We can choose here any harmonic, but commonly used also the 5th harmonic. So the setting over here is that it is the harmonic setting over here, which is second harmonic, and the 5th harmonic over here. Both of them will work together. Means we will test first, second, and third. But there is something here that we need to take care. Like I need to ramp to operate or ramp to not operate. Some people need to ramp from operate, means from blocking to operation. Some people want to ramp it from operation to, let's say, blocking. So that's the difference. Like in second harmonic, the relay have to operate under 20% and block over the 20%. So this is how it works, how the people need. It depends on the site and the engineer, the need of the engineer. Now, it is very important for the harmonic, for the phase relationship. And this is only a quick view about the harmonics. Like always in the fundamental, you have positive, and the second harmonic you have negative, and the third harmonic you have 0, and then again fourth harmonic. That's why it's not used. Again positive, and then we have negative, and the sequence goes like that. So we'll have positive, negative, 0, positive, negative, 0. So it is very important to know what do you need. You don't need positive because during the fault it is negative, and 0 depending on the fault. It is phase-to-phase, 3-phase, whatever. Now this is something like what we are generating, because our equipment can generate harmonic up to 4 frequencies in same injection. Means that we can superimpose those harmonics in same injection. Like it's the same phase, I can put 4 frequencies together to end up with something like the harmonic we have seen here. Now this is, if you see that it is phase A is showing good, but phase B and C showing a bad harmonic, and that's because of pure, or not pure, sorry, wrong setting. Now if we change it, the harmonic waveform, that's what we'll have here. That's the difference between both harmonic you see, both phase B and C. Now it's the same thing that you can do the harmonic for the third harmonic and other harmonic. That's some only examples about how to view them. Now after we just put only the setting over here, which is what we need, and we can go directly to the test screen. The test screen will go for winding 1 and winding 2 and test the harmonic according to our setting and check the behavior and pickup for that for the second harmonic. But for the fifth harmonic, it will go short, means one shot like operation and one shot not operation. It will check, like in our case 30%, it will see there is no operation 30 and there should be operation for 20. That is only a short test for the fifth harmonic. That is all for the transformer protection. Now we will talk about the breaker failure protection. Now, breaker failure is something different. That the breaker failure means that the breaker, we have a tripping, the breaker fails to open due to maybe there is no DC, maybe the trip coil is defective, maybe the tripping cable is not reaching to the breaker, a lot of things depending on what you have. Maybe the mechanism is having a problem, a lot of things, but we need to protect our network against those things. So let's say that we have a fault, breaker 3 didn't open. So what is going to happen now? The breaker failure has to send another command, because as soon as the protection starts, it will send to breaker number 3, and if breaker number 3 did not open, the same signal is going to a breaker failure to start. And depending on the scheme and the quantity we have of current, breaker failure of breaker 3 should start, and then it should resend or retrip the same breaker. After retripping the same breaker and the breaker did not open, it has to go for other thing, which is tripping all surrounding breaker. That is to make sure that all the source coming through to the fault is open. Means this is not open, we have to open these two plus this. That is all sources to the same breaker. And this is how it works. And suppose that we have a remote, even remote trip will go over there. That's how the breaker failure operates. Now, what do we need, or what is the components we are working with? It's like current detector and timer of breaker failure, these two things. Now, the current detector will detect the current flow, which is we need the pickup, as we said, if it is phase or three-phase or it's the ground. And then we have also a 52A contact, which is used in low current mode, or let's say for the transformers, generators, because in that cases, if we have a fault, we are not supposed to wait for current. Only 52A contact is enough, plus initiation from my tripping over there should start the breaker failure. This is the basic breaker failure scheme, that we have a breaker failure current detector detects current, which is already, we have it, let's say, more than the setting. And then we have a breaker failure initiation, which is from my protection relay, sends the trip to the breaker plus 2 to start the breaker failure at the same time. So both of them starting will go to a timer, and this timer, after elapsing the time, it should do it works, means it has to trip the same breaker or it has to trip surrounding breaker depending on the scheme. Now, this is a basic timing chart of that. Like, because doing the timing is very important. If we mess up with something, your breaker failure may misoperate. And that is really going to have, going to have a blackout because of that. And if you increase the time, again, you may have problem like extending the fault time, which will destroy some equipment and will have an effect. So it is basically the protective relay time, which is your relay operates. Now, and then what is going to happen? This is the breaker interruption time that the breaker should open in here. and then it should reset everything here, up to here. The thing is that the same time when my relay operates, it sends to my breaker failure. Now my breaker failure time will be up to here, because if the breaker did not open, then we are putting the breaker interruption time, the current reset time, plus the margin time. If all this, the breaker failure time at stage 1 should be more than these. If the breaker did not open during this time, breaker failure time will retrip or trip depending on the scheme. That's how it works. Of course, it will retrip same breaker, as I said, at stage 1, and then stage 2 will send a command to nearby breakers if required. Now, this is some of the failure modes of circuit breaker, which is circuit breaker contact did not open, or let's say did not open fully, or short maybe in the trip coil. This is some of the failure mode. Mechanical problem, as I said before. Or failure to clear, like it's contact open but fault not extinguished, so we have still fault inside. Current continues to flow. That is something also that we have. This is some of breaker failure modes that we have faced in the field. Now the minimum fault current, as I said, that if you remember with the this one here, that they are AND gate, because I'm waiting for current plus the initiation. That's for the normal breaker or normal feeders. But for generators, the transformers or harmonic filters, no. It is totally different. We are having the breaker failure over here start, but we have an OR gate over here for the current or circuit breaker. Means if my circuit breaker close, we'll have continuous signal over here. If we have breaker failure initiation, it will go directly without waiting for the current. And that is commonly used for, as I said, for generators and transformers. And that's to protect it, because current detection for the transformers and generators, sometimes it is very minimal. Now testing the breaker failure, that we have to do it with our sequencer. Our sequencer will have to create some sequences so that we can do the breaker failure. The pickup of breaker failure is like an overcurrent, but the timers behind that we have to do it right, which is the very important thing to finish. Now, we'll use the sequence mode to do the breaker failure testing, as I said, and it's very easy. Just create some modes. Now, I have created something like this is for BF number 1 and BF number 2 as my timers. And then this is CB contact or BF INI, which is initiation from outside. So this is a common thing that we need to do so that we can have two timers. It's only one you don't need here, so it's only you have to connect only one timer. But BF INI we need. So as you see, the quantity that I need a current over here plus BF INI, then I have BF1. And if I need CB with current or not current for the generator, then I can have BF1. And if I have breaker failure stage 2, which is timer 2, and then that's why we have it here to measure both timers together. This is an example from RICA, which is ABB, famous breaker failure relay. And we can see also over here that from the current over here, which is going inside, we have an output coming here, which is combined to AND gate. And this AND gate is waiting for initiation from here, which is coming from the protection relay. So whenever we have a trip from protection relay comes to the AND gate, and if the current is more, then this AND gate will energize this relay after time. And this, which is timer over here, this stands for timer, and then which will give me a trip output, and depending on us where you want to trip. So this is a typical breaker failure relay that we are using everywhere here in, let's say, in Saudi Arabia. So what I have done here, we have done a circuit breaker close, and then this is a stage 1, and as stage 2, I put BF INI with the current over there, and then I'm waiting for my trip as BF number 1 to have the timer. And if that did not clear because the breaker is defective, there is no DC or whatever, it will go for BF number 2, and it will wait for the contact to trip, and then I'll have my timer number 2. And same time, the breaker is closed, and still I have the initiation, means the voltage is hit. Then after that, of course, the breaker failure, which is the current go away, and my breaker failure initiation gone because it is voltage clear and contact is open. Now this is very easy, and then that's how we are testing the breaker failure. How we are testing the breaker failure timing. The good thing here is that we will have 2 timers, of course. From the timer menu here, we can set up these 2 timers, like when we need to start and when we need to stop. So we'll have the correct timing over here. Not only that, when we have it finished in our test report, we can rename it as BF test, and then we can use it as template to repeat any breaker failure condition. And that is from here that we can repeat the test. It's our template. We can use it anytime. And if we need to edit the values, we can come here and edit, which is going to be very useful to do any breaker failure. It's only by knowing that we need the contact of the breaker, a contact for the breaker initiation, and 2 contacts to trip. So that is how we are working by the RTMS to do the breaker failure testing. Now next we will talk about sync and auto recloser relays, and those relays usually also both of them are together, but sync is used also in separately than the auto recloser. So both of them can be together, or sync can to be separated. So what is sync relays? Sync relays are the synchronizing relay between 2 different sources, and these 2 different sources we need to make sure to close to avoid any problem, any, let's say, unwanted difference in voltage will create a fault, will create anything to be matching. And these matching, it should be like voltage magnitude should be the same, frequency should be the same, and phase angle should be the same, or all of them should be within a limitation depending on the calculation over there. This is something like we have a 2 different system, then we have breaker we need to close, like 2 different generators. So we have to match the frequency, phase, and voltage. Otherwise, we cannot close. If we close 180 degree, we'll have a short circuit that will destroy a lot of things. If we go ahead like more than that or less than that, depending on my calculation or the engineering calculation, it should be within the calculation. If it is more than the calculation, it may affect some other components in the network. Now, how to test it? We have already a ready-made, let's say, scheme that you can test with, or icon here, and this will test the synchronizing very easy for you. Just we put the system voltage, which is system 1 and system 2 details, and then we come here and put the frequency. We have the frequency, delta voltage, the voltage difference, and also the phase difference over here. So what we need is, that's what we need. We need the frequency, voltage difference, and phase difference. From here, only those quantity we can test these 3. This is going to be the future, not now. That's for the synchronizer relay, which is for the generator usually, which is having some different thing. And then we can even check the output contact, which is we send it to the governor or the excitation. So that's something later on we'll have. But now we are only working with this side. Now this is what we are going to end with. So we have 3 icons below. One is for quick test, dynamic, and point of origin. So what is the difference and when shall we use each? The first quick test will check the 2 quantities separately, means it will check the voltage and then it will check the frequency. That's from here, that's the voltage here and the frequency here. So this will check the frequency deviation, this will check the voltage deviation. But I need to check both together, like voltage and frequency. Of course, the phase angle is always common between them. Then we can go for dynamic. Dynamic will have the possibility to check both quantities together, means it will check voltage, will vary voltage with frequency together here. And we have the point of origin, means it will come up to the point of origin over here. That is only extra, the same, but something extra. But we can run only like voltage, or we can run also from the same menu, which is here. We can run only the voltage, we can run only the frequency, or we can run only frequency or everything. So that is some option that we can go through also to test these things. That is for the synchro relays. And for the auto-recloser relay, now why we need the auto-recloser? Again, it is something to make stability for the system. That's if you have, you know, all the faults, maximum 80 to 90% of the faults are transient faults. Means those are not having issue that you can also directly close or close back the line. So these auto-recloser are designed for this, to keep the power on always. So will not have effect to anything. And this is an only small example. Like if we have a fault over here, then our main relay will trip, and same time our auto-recloser should start the breaker again after some time, depending on our setting over there. Now, how to do that and when and where, that is something that we need to do. And how many shots, because this is very important. Like, I need to close the breaker only 1 time, 2 times, 3 times, and under which conditions? 1 phase, 2 phase, instantaneous, over. So a lot of things. Commonly, our standard says only instantaneous faults should do that, but over current fault, which is time delayed, we call, should not do that. And that is because time delayed means there is a fault really over there, but transient, which is instantaneous, there is no fault. Maybe it's because of a 3-phase down over there, maybe something transient like the bushing is not cleaned well, or maybe there is a lightning over there, so something like this. Now, we have 2 types, or not 2 types, actually we have multi-types. We have a single shot, we have 2 shots, 3 shots, so it depends on the configuration of the auto engineering and why they need it. And if they need only single shot relay, for example, that means that it will, whenever we have a fault, it will only close it 1 time. And then it will wait for a time, and between this time, which is reclaim time, the fault still there or coming over there, then it will go directly to block. So there is something like we have 2 different quantity the auto-recloser will work with. Auto-recloser also can be a single phase or 3 phase, meaning that it will work as a single phase auto-reclosing. Means if in Europe, as far as I know, when they have a fault, they usually trip same faulty phase, but other 2 phases will be still healthy. So the same phase will be auto-reclosed. And in this case, it doesn't need synchronizing because the other 2 phases are already synchronized. So directly it will close the other 2 phases. But in case of 3 phase, it requires synchronism relays. And these synchronizing relays, again, we have to go to the same quantities we just talked about, like the voltage, the frequency, and the phase angle, which also going to be affecting the auto-recloser time. Now, testing the auto-recloser is going to be also with the sequence. And when we create the sequences over here, it's going to work similar to the breaker pair we have talked about. So it depends on how many states we need, and we can rename it to anything we need. And I have done something like that, like we have trip 1, reclose, trip 2 means my protection relay will give a trip, and then we'll reclose after some time, trip 2, whatever we need. So it is something that sequences we can do. And after finishing the sequence, again, you can save it as the AR test. You can repeat the test from here. We can edit, changing by something. So it is something that we have to understand first how to do it, how our relay is operating. Then we can implement it. After implementing over there, we can repeat the test, or it will be our template.